invite Sujeet Kumar Singh from National Institute of Science, Education and Research. So he is going to talk to us on congruences in Hermitian Jacobi forms over Qi. Please, Sujeet.
Thank you, ma'am. First of all, I would like to thank the organizer for giving me the opportunity to speak here. So this is my joint work with Dr. Javan Meher, and in this presentation, I am going to discuss about UP congruences in Hermitian Jacobi form over Qi. This congruences has been already studied in modular form and Jacobi form, so I will start from modular form. So by H, we will be denoting the complex upper half plane. A modular form is a function from H to C, which satisfies the following two properties. The first is a modularity condition, and second is that it has a Fourier expansion of this form. So it's form a vector space over C, and we denote by I will be following these notations that by Mk we denote modular form of weight K, and Mk are when collection of all the modular form which has a Fourier coefficient in R, where R is any ring R subset of C. Okay, so Ramanujan delta function, which is defined by this. So it's a modular form of weight 12, and it has Fourier coefficients in Z. Next, I define what is called UP congruence. So we will be taking P to be a prime and ZP to be the localization of Z at the prime ideal PZ. So if we have a modular form which has Fourier coefficient in ZP, we define the UP operator as by this way, means we take out those coefficients such that P divides N, and we say that F has a UP congruence if F slash UP is congruent to 0 mod P. So this congruence means all these coefficients will be congruent to 0 mod PZP. PZP is the maximal ideal in this ZP ring. Okay. So I give some example of UP congruence. So we have delta slash UP is congruent to 0 mod phi for this primes. So this was proved by Ramanujan in 1960, and for P equals to 2411 by Newman in 1972, and for this big prime by this Lygros and Rogier in 2010. And these are the only primes which are for P less than 10 to the power 10, such that delta slash UP is congruent to 0 mod P. Even this is a conjecture that there are infinitely many primes such that delta slash for the conjecture, but I will discuss about some equivalent condition for the existence of UP congruence in modular form, and then in my case in Hermitian Jacobi form. So next, so to give the equivalent condition, we uses the mod P theory. So this was proved by Swinnerton. Suppose that we have two modular form, and they are congruence mod P, then their weight must be divisible by weight difference must be divisible by P minus 1. So the two modular form of different weight can be congruent mod P. So it's interesting to define the smallest weight modular form which has a congruent to a given. So we define for some bigger class. Suppose if f is any function which has a Fourier expansion of this form with the Fourier coefficients in ZP, and if f is congruent to some modular form of weight k, then we define the filtration to be the infimum of weights of all the modular form which are congruent to this f mod p. Okay. Next is a theta operator. Suppose we have a theta operator. Theta operator is defined like this, and if f is any modular form, then if we apply theta on this f, then it simply give the Fourier expansion of this form. Theta f is not a modular form, but Swinnerton have proved that this, if f is any modular form, then there exists a modular form of weight k plus p plus 1 such that theta f is congruent to g mod p. Now since this theta f is congruent to g mod p, and the way we have defined this filtration, we can calculate the filtration of theta f. So Swinnerton I proved that that filtration of theta f is always less than equals to w of f plus p plus 1, and it has equality if p does not divide W of f. Uh, Ono used these two results, this result and this result, and give an equivalent condition for the existence of UP congruence. So the result says that if f is any modular form and f is not congruent to 0 mod p, if you take p to be greater than k, then f has UP congruence. This f has UP congruence. If you calculate the filtration of this thing, this theta p minus k plus 1, if it's equals p minus k plus 3, then f has a UP congruence. So he gave an equivalent condition for the existence of UP congruence in modular form. So next, similar results hold in the Jacobi form. So first I will give the definition of Jacobi form. A Jacobi form is a holomorphic function with matrix index m, uh, sorry, from H cross Cl to C of weight k index m is for the Jacobi group SL2G semi-direct product ZL cross ZL. If it satisfies the this is transformation with respect to the group SL2G, and second is that it has a lattice transformation with respect to ZL cross ZL, and third is that it has a Fourier expansion of this form. Okay. So I will be following this notation that by JKM gamma L, we Jacobi form of weight k index m, and R when we put the collection of all the Jacobi form and the Fourier coefficients in R. Similar result in the case of Jacobi form with matrix index for UP congruence also have been proved, and for Jiggle modular form also this was proved by Martin Rom and Olive Character in 2015. And the main result which was needed to prove their result is a structure property. It says that suppose if phi is any Hermitian Jacobi form, and if determinant of 2m is t, then there exist phi I Jacobi forms, phi I and modular forms such that phi can be written like this. And if psi is any another Jacobi form written in this form, and if they are congruent, so this results breakdowns to fi is congruent to gi mod p. So any two congruence of Jacobi form, if they are congruent, then their corresponding fi must be fi congruent to gi mod p. So using these results, they have proved the result for similar result for Jacobi form with matrix index. Uh, we have proved UP congruence for Hermitian Jacobi form over Qi. So I will first give definition of Hermitian Jacobi form over Qi. So these are notations we will be following. We take gamma 0 to be to gamma O semi-direct O square, and this is the Jacobi group in the case of Hermitian Jacobi form. So it's a function from H cross C square to C, and it satisfies the with respect to this group, it satisfies the modularity transformation, and it has a lattice transformation, and it has a Fourier expansion of this form. So we will be following this notation that by SJKM delta, the space of Hermitian Jacobi form of weight k, index m, and parity delta, and by R, the collection of all the Hermitian Jacobi forms of weight k with all the Fourier coefficients in R. So similar to the case of modular form, we proved that if two Hermitian Jacobi form, if they are congruent, indices must be equal, and their weight will be divisible by weight difference must be divisible by p minus 1. Moreover, we have proved that if there is a collection of finite sum of Hermitian Jacobi form, and if they are congruent to 0 mod p, then for each conjugacy class, this class summation will be congruent to 0 mod p. So to prove this, we followed the similar method as we have in the case of Jacobi form. So this was not a big problem for us. Next, we defined the filtration as we have in the modular form. So suppose phi is any function from H cross C square to C, and it has a Fourier expansion of this form. And if phi is congruent to some Hermitian Jacobi form, then we define its filtration to be infimum of all the weights of modular form which are congruent to this phi. And similar to modular form, we have a heat operator in this case, and if we apply this heat operator on any Hermitian Jacobi form, then it all again give a Fourier expansion of this form. So next, as we have in the scene in the case of modular form, we needed to prove a similar result here for Hermitian Jacobi form, and this was the big problem for us to prove. And the proof of this theorem requires a structure property, as we have discussed in the case of Jacobi form. So this that structure property is not known in the case of Hermitian Jacobi form. And to overcome that problem, we consider a bigger class of Jacobi form. We consider the Jacobi group to be gamma 1 O, and Jacobi form for this space, this group satisfies all the condition of Hermitian Jacobi form with epsilon equals to 1. So there it was epsilon to be 1, minus 1, I, and minus I. So here we take only epsilon to be 1, and it satisfies all the condition of Hermitian Jacobi form. And moreover, the Hermitian Jacobi form, now it's become a subset of this bigger Jacobi group. And then we prove that uh, this Jacobi space is isomorphic to Jacobi form with matrix index with M equals to this group as a vector space over C. And then we extract the structure property from here to this our vector space. And we prove the required result for this. And next, if you define the filtration for this space by suppose if phi is any function which has a Fourier expansion, and if phi is congruent to psi for some Jacobi form in this space, then if you define filtration for this space by W phi, then we prove that if phi is any Hermitian Jacobi form which is a subset of this, then we prove that these two filtration, this was filtration with respect to this space, and this is a filtration with respect to this space. So we have proved that these two are equal. And using this result, we have proved the required result in the case for which we were required. And then using these two results, we have proved the uh, so first I will define what is UP congruence in this Hermitian Jacobi form. So if phi is any suppose Hermitian Jacobi form which has a Fourier expansion of this form, so Atkins UP operator on phi in this case we define by this way, that it takes out those coefficients such that P divides 4nm minus norm of R. So we say that phi is UP congruence if phi slash UP is congruent to 0 mod P. So we proved the similar result as we proved by Ono, that phi is any Hermitian Jacobi form, and if P is greater than K and P does not divide n, K greater than equals to 4, then phi has UP congruence if the filtration of this element is P plus 5 minus K. Okay, so Hermitian model of Hermitian Jacobi form actually occurs as the Fourier Jacobi coefficients of Hermitian modular form. Hermitian modular form is has a Fourier expansion over Qi has a Fourier expansion given by this, and it has a Fourier Jacobi expansion. Any Hermitian modular form has a Fourier Jacobi expansion of this form. So this phi km is equals to this much, this Fourier expansion. And these phi kms are Hermitian Jacobi forms of weight k, index m, and for some parity delta belonging to plus and minus. So using this property of Hermitian modular form, we have proved a similar result of UP congruence in the case of Hermitian modular form of degree 2 over Qi also.
Okay. Thank you, Sujeet, for such a nice talk.